Today we're going to continue with probability, but we're going to take one step into the camp of inferential statistics and deal with the distributions for sample statistics. We will first talk about the link between simple random sampling and sampling distributions, then discuss what point estimation is, well, define it really. Then we're going to try to hammer home what in the world a sampling distribution is, and that's before we turn to the examples of sample mean and the sample proportion. And at the very end, we'll have about 5 minutes worth of more theory before we do problems. So it's a fairly, it's not that long a subject, but parts of it are painful. So I'll point out when we get there, though. Didn't know already. Okay, so we're going to start out with a certain amount of just theory. Several slides of just a lot of text. Because we need to make sure everything's figured down. Everything we deal with from here on out is going to be inferential. We're going to talk about taking a sample and inferring to a population. That's the key point of what we're going to be doing. Naturally, the sample will only give us an estimate. The question then is, how good is that estimate? Well, we are using the sample. We use the sample mean because that's our primary tool to estimate something in particular, a parameter. In general, any sample statistic can be used to estimate some corresponding parameter in the population. So to review, a parameter, it's a number, doesn't move around. Its only flaw is that we don't know it. Okay? So for instance, if you want to know the percentage of $250,000 less homes that is in arrears by more than 2 months. Well, you could use that as sort of an indication of just how much trouble there is in the mortgage market, right? The problem is there's no way you're going to get that data. You can't very well talk to the mortgage companies or to well, the banks probably have some ways to help each other get accurate data, but I'm not really sure if that would constitute collusion. Anyway, my point is it's something you'd have to estimate, because even if you got most banks to cooperate, you would have to try to compare notes, and there'd be all sorts of problems with it. So there's something out there that you're interested in, the parameter, it's unknown, and instead of actually doing a census, you estimate based on a sample. You look at specific homes, and you go and interview. So the question, again, is what is a good estimate? Not just what is a good estimate, or how good is it? And then we have to ask the question, well, what does good mean in this context? And usually that means that we have not only an estimator that provides a trustworthy, relatively trustworthy number or estimation, it tells us something about how likely we are to miss by a certain amount, by a significant amount. So naturally, these are fairly tricky questions to deal with. There are several ways we can approach this, but first we need to talk about what we can and cannot do with different types of populations and different types of procedures. We're going to limit ourselves to simple random samples, although we will discuss certain alternatives towards the end of the lecture. With a finite population, every single member of the population must have the same probability of being selected. It's in a finite population. Typically, we would sample without replacement. Can you imagine going to the same home 30 times in a row and asking about their foreclosures or their financial situation? Obviously, they probably wouldn't cooperate more than, if they cooperate once, that's good. Twice, it would be surprising. So typically, we would sample without replacement. But it is naturally possible to do sampling with replacement. And as an alternative to a finite population, you could have an infinite population. So let's take that first. Finite versus infinite population. Which one do you think is easier to work with? Because?
sample.
Percentage of the population? That's true. Why does that make it easier?
You mean more accurate on your result?
That's a good point, but that has to do with, well, clearly accuracy rather than ease. Yes?
We go with infinite.
Because?
The formula's shorter.
There we go. Yes. It turns out that the infinite population is simpler to work with, simply because the math works out very nicely. Similarly, with replacement or without replacement sampling, it turns out that what ends up happening is even when you do sample without replacement, you pretend that you're sampling with a replacement. Usually. With a large enough population, it makes no difference. Like, imagine you're dealing with the US, the population of the US. Then it really, I mean, the probability that you get a sample that has the same person in it several times is virtually nil. So you basically do your sample, and then you treat that sample as if it's representative of something that you have, or a procedure without replacement. And it turns out also that that's a conservative approach. So you typically get stronger results if you interpret it, it's harder to show that you have something significant when you pretend that you're sampling with a replacement. In other words, if you get a result using sampling with replacement, then you would get a significant result sampling without replacement. And therefore concluding by using the easier approach is simply strengthening your conclusion. So it's perfectly valid. We're actually not cheating here, although we are making our life easier. Speaking of cheating, when we draw a sample, how would we make sure it's random? That's the next point here. Computer-generated random numbers. We use them quite a lot, but are they truly random? And why not?
They usually work off the seed value.
What's that?
They usually work off of the seed value.
Very good. And that seed typically comes from
Person.
where?
Time, date.
Right. So it looks like it's random because, you know, the time changes all the time, obviously. And once you enter in this time as a seed, you get a different number each time you access that particular type of function. But it's still pseudo-random because if you code, literally write down the seed inside the functions, you're going to get the exact same set of numbers each time. That has actually advantages as well as disadvantages. If you're comparing two different systems, you do want to make sure that you're comparing apples and apples. And so you force the same set of random numbers, pseudo-random numbers, to each model, right? You make a change, do the simulation again, but with the same set of random numbers to see if your change actually has an impact. That's perfectly acceptable. But in a lot of cases, in particular when you're doing random sampling, it can be questionable. And I forget exactly who, somebody told me this semester actually, that now there is a way to get random samples from the web. In the past, it was possible to do by observing the number of cosmic particles that hit some sensor in a certain time frame. But apparently somebody has done that and made it accessible through the internet. I believe it's at random.org. And I apologize if somebody in this class told me that. But I just don't remember who told me. Okay, so the infinite population. The difficulty with the infinite population, though, is of course you can't exactly assign the same probability to each member because you'd be assigning a probability of 0. So that's not terribly useful. What you can instead think about is that the population is represented by some distribution with a mean and some standard deviation. Every single time you go and draw an observation, you go back to the well, you pick one, and then you put it in your sample. And then, of course, your population distribution hasn't changed. It's still there. It's called a data generating process. And that actually makes life pretty easy, in particular because you now, of course, have your parameters right in front of you. It's easier to think about. But it can be a little tricky to work with, especially if you're trying to generate data. Okay. Point estimation. As opposed to what? Well, I guess that's a rhetorical question. The point estimate or point estimator is always just a number. So if we're trying to estimate a population mean, we use the sample mean. If we're trying to estimate population standard deviation, we use the sample standard deviation, and so on. What do you think is the difficulty with a point estimator, or weakness? What is the probability that your point estimator actually hits a population parameter of interest?
It depends on how large the sample is. Is it a large?
True. And the larger the sample,
The closer it is to the population.
the closer it is, but the probability,
Smaller. The larger the sample, the smaller.
not necessarily. Let's say that your point estimator itself has some continuous distribution. In that case, the probability that it actually hits the population parameter is 0, right? The probability that any continuously distributed random variable is any particular value is 0. So that's kind of an issue. It can be regarded as one. So we turn to sampling error. Sampling error essentially just tells us how much we missed by. So what we can do is calculate probabilities that the sampling error is more than some number. And that's usually somewhat fairly useful because you can usually compare an absolute value, such as any of those, and decide whether or not the sampling error of 10 is acceptable in the context of your problem. I can't make a broad, general statement right now, but in the context of a problem, you typically can. Like, for instance, if you're trying to deal with miles per gallon, if you have a sampling error of 0.001, I'm pretty sure nobody cares too much. But if your error is 50 miles per gallon, then you've got a problem. Okay, so today we're going to do step 1, basically, to get to the full set of inferential statistics tools. We are going to work with sampling distributions, and we're going to know everything there is about the parent population. Kind of like inferential statistics wheels, in the sense that we know what we're looking for, and next week we're going to take off the training wheels, and we won't know what we're looking for. Today, though, this is how all simulation is done to test whether or not a method works. You decide, you specify a population, and you check to see whether or not what you're doing makes sense. So we're going to look at two things: a mean SAT score from 900 applicants, as well as the percentage that wishes to live on campus. There are essentially 3 ways we can do this. We can either do a census, or we can do a pseudo-random sample of 30, or well, any sample, or we can come up with a truly random sample of 30. Does anyone know what a random number table is? Does anyone use one?
No.
You have?
I'm old enough to have used one, yes.
Okay. In what context?
In the stats course,
Oh,
20-something years ago.
okay. Well, actually, I'm old enough to have used communicators that literally ran through less than 1 byte per second. So I'm starting to feel like antique at times. But moving on, the random number table. My understanding of it is that it's created, or was created, by someone doing something truly random, like rolling dice, and making notes, writing down these random numbers. But then they're just kept, right, in a book, and the book is sold. And if at any time you need to generate a certain number of random numbers, you just start where you ended last time and pull the works. I'm not sure that it's considered terribly elegant anymore, but it definitely works. And of course, it's, once you've got your numbers or your book, it's not that random, but you're not supposed to cheat and look ahead. Okay, so let's look at our census. In the census, we find a mean of 990 and a standard deviation of 8, and 72% want to live on campus. Okay, so if we knew that, of course, there would be really no purpose to doing the sampling. But what we're really doing now is we're talking about how does sampling work. We're not actually trying to estimate those numbers, because now we know them. We want to compare to X bar and people. So we take a sample of 30 applicants, and actually, I should de-emphasize the table. I'm not going to use that. When it comes to generating a sample, the simplest thing that I can think of is to use Excel, although that definitely has weaknesses. There are better approaches, but if you just have your list of observations, or your entire population, in a column next to it, you just enter this function. You sort on this column and take the top 30 or top 40 or top whatever you want. And that will give you a pseudo-random sample of whatever you need. Very simple, and at least it's transparent. Unlike if you're dealing with maybe Tab or SPSS or SAS, in which case often if you're asking for a random sample, it'll do something similar, but you don't really know what it's doing. Okay, so you calculate a sample mean. You find 30, you add up all the SAT scores, you divide by the sample size, and you get 997. The key question now is, are you surprised?
No.
No? Why not?
It's not exact because it wasn't based on census data, but it's close.
Okay, good. I would actually tend to agree. But the key question is, how do you know that it's close? How do you measure closeness? That's not an obvious, or the answer is not obvious, right? And the same question goes for the standard deviation and the proportion. Proportion here, 68%. It's not 72%, right? But is it close enough for you to think that, it wouldn't be surprising? It's not a question of collecting. I mean, it could have actually been 1, right, or 0. Because there's 72% that wanted to live on campus. You can easily get a sample of 30 where everybody wants to live on, or everybody wants to live off. Question is 68% surprising if 72% is the true proportion? Okay, that question, is 997 surprising? And to what degree is it surprising? Is really the core of today's fun and games. And in fact, okay, so we're dealing with a population. We gather our sample, we calculate X bar, and we use X bar to say something again about mu. So the question is, what is X bar? Before we gather our sample, what kind of an animal is it? And I'm starting to be convinced that this is roughly the point where I lose about half the class typically. So we could be here for a while at this particular point. What kind of animal is X bar before the sample is collected? Or if you prefer, you can tell me what kind of animal it is after you've collected your sample.
It's supposed to indicate the average of the bigger sample.
The population?
Yeah.
It is true. Are you talking about before or after the collection of the sample?
I'll say after you take the sample and calculate the mean.
sample mean, then you have a number in front of you, right? Okay. That number doesn't move around, does it? Okay. So that's really the answer to the second question. What is the sample mean once you have your sample? It's just a number. You hope that it represents the mean of the population. I agree with that. But that's more of a pious hope than anything else at the moment. And it also begs the question, what is the sample mean prior to collecting a sample?
I mean, there isn't really that far after the sample, a subset of the overall average subset, an average subset of the number of random sample points you've taken of the entire. So I mean, you could say it's only represents 30 of my entire sample size average
After you've collected?
after you've collected.
Sure. The question then is, how does the sample mean relate to the population mean? That's the sort of the point of today's entire lecture.
It represents it in that, you know, if you did a proper sample size and truly randomly picked from your population, it should be fairly representative, right?
Okay, so by fairly representative, you mean that the sample mean should be fairly close to the population mean?
Correct.
Okay, I agree with you. But that still begs the question, what is the sample mean prior to the collection of the sample?
Doesn't exist, does it? Prior to the collection of the sample?
How did it get it? Prior to, how did it even be there?
Well, okay, if you really want to talk about whether or not numbers or functions or constructs can exist, I mean, that's a philosophical discussion for, I think, significantly more alcohol than we've had.
We can fix that.
Yeah, true. Nevertheless,
Didn't you take the maximum value that you could possibly get and the minimum value you could possibly get, random, you know, come up with something like that? You could take the average of that and say, well, that's my prior sample average?
very good. Okay, so you can come up with a minimum, like, let's deal with the population proportion versus the sample proportion, because it's easier to think about in that sense. With a 72% out of a 900, that's, well, that's certainly enough members so that you could come up with a population of 0 in your sample, or, I'm sorry, a proportion of 0 in your sample that want to live on campus, or a proportion of 1, right, in your sample. Okay. So what you're saying is, well, we come up with a lower bound and upper bound, so that's 0 and 1, and then we take an average of that, so that's 50%. I like where you're going with it, it's just not entirely, you're not quite there yet. Because the lower and upper bound, those are extreme values, right? Don't you think it might be more likely that you're gonna see values closer to the middle of some sort?
I mean, you just don't know what the sample is that you're taking a sample. I mean, what if you're sampling everybody that's already at the extremes?
No, you're sampling at random, remember? It's a simple random
I
sample.
mean, you don't know if what you're sampling out of is, you know, at the extreme, like everybody the sample, the random sample you take of how many of our students, they all wanna live in that building, let's say. That's the best, you know, place
Well,
to
but
be.
remember, 72% of the 900 students want to live on campus.
Oh, yeah. Oh, so you're saying use that data to do your prior sampling?
No, what we're trying to do here is to come up with a conceptual picture of what the sample mean actually is. And you can tell, I mean, based on the conversation we're having, this is not a trivial question, right? But it's a crucial one. If you understand what the sample mean is, then this is gonna be easy. And conversely, if you don't, this is gonna be really hard. So let's pursue that a little further. Now, right now, we know what the population looks like, right? So we can come up with those bounds. Typically we can't, but right now we can. My question to you is, wouldn't it be more likely that you're gonna get population proportions in some way or shape or form related to the middle or close to the actual population proportion than the bounds? Make sense? Okay. Now the question becomes, can you assign probabilities to the different ranges? Not you personally, but can you imagine that it's possible to assign probabilities? Okay, so, conceptually, we have a process whereby we collect 30 observations, we calculate a sample mean, we can assign probabilities, if not to the exact sample mean, then to intervals of the sample mean. What is that starting to sound like? Yeah, I know. You're right about that.
No, but basically your standard deviation, where more is gonna be in the middle and less and less.
A normal distribution.
Out of
Not so much a particular distribution as, let me rephrase. So getting your sample, collecting that, the process, right? You collect your sample and you calculate a sample mean. That's a process whereby you get an outcome that is not predicted. You can't know with certainty what the outcome is going to be. We had a term for that. What did we call that? I'll give you this one. It's an experiment. We conduct an experiment. We, again, gather a sample. We calculate a numerical outcome, and we can assign probabilities to those numerical outcomes. Right? That's basically what X bar is before you gather a sample. So, what is that starting to sound like? Okay, let's try a different tack. Let's say that everyone on this planet is either in favor of strawberry shortcake or not. And there's a 50% probability that you pick somebody who's in favor, and a 50% probability you pick someone who's not. And there's nothing in between. You either favor this or you don't. So, what is the smallest possible sample size that is not completely trivial? Okay, the smallest size, I'll give you a hint, the smallest sample size that's completely trivial is 1, right? 2, right? Because 2, you can at least calculate a mean that's not equal to the single observation you're dealing with. So, we're going to call our favorability index X. We have 2 observations, and the degree to which strawberry shortcake is favored, which is again either 0 or 100%, is going to be labeled with or captured in X, X1, X2. So what are the values we could have? 0, 0. So this particular sample would indicate a great deal of hostility to shortcake. 0, 1, I guess that would be indifference. 1, 0, still indifference, and 1, 1. And the world is full of cake. Okay. Now, think of this as sample 1. If this is sample 1, what is the mean in sample 1? 0, good. 0 plus 0 over 2 is equal to 0. How about here? 0.5, 0.5, and 1. Everybody see that?
Mm-hmm.
Okay. Now let's change the rules just a little bit, just for fun, and say that 60% are in favor of strawberry shortcake. If that's true, what is the probability that we saw this sample 0.4. That would just be this one, I'm talking about the whole sample.
Zero.
Not zero. Okay, so in order to see the sample, you first have to pick one person who is not in favor of strawberry shortcake. Okay, it's probably confusing to change the probabilities midstream, so let's keep them with 0.5. You pick one person that is in favor of, not in favor of strawberry shortcake, right? And now you pick another one. First one has a probability of 0.5 of not being in favor. The second one has a probability of not being in favor. So in order to get the probability, how much? Exactly. Because of, you're right, but what's the reason? In order for that to be true, we need,
Multiplication.
we're multiplying, and why is it that we're allowed to multiply two marginal probabilities to get a joint probability? Can't hear you.
I'm sorry, permutation, is that?
Well, that's not why we're allowed to do it.
That's what you do.
Independence?
Independence. Because we have independent draws, we have a random sample, we have independence, and we're allowed to multiply together marginals to get a joint. So this is 0.5 times 0.5, or 0.25. And by the same argument, they're all 0.25. All the sample points. But we notice that we have two different samples that both have the same sample mean. And that's perfectly possible, right? If we're thinking back on our applicants, you could easily have two different samples with the exact same mean SAT. So we end up with and the different values are 0, 0.5, and 1. What are the probabilities?
0.25, 0.5, and 0.25.
Excellent. Okay, any questions about how we got here? Make sense? Okay, now, what is this animal? Numerical outcomes? Probabilities. We call that something very special. Starts with an R. No? Really?
Relativity?
Huh? Relativity. Wrong class. Wrong, entirely wrong school, in fact.
Although it does bring us back to the alcohol, so.
No, the R we're talking about is random. Random. And what's the second word? Random. Variable. X bar is a random variable. Remember that? Numerical outcomes? Probabilities? No? Okay. Well, we do have a probability distribution here, right? Is it discrete or continuous? In this case?
Discrete.
Discrete, yes? Okay. So, this exact same thing holds if you're dealing with a population of 900 and you're pulling 30 at a time. The problem is if you were supposed to list all the 30 different X's and all the possible scores they could have for SATs, you'd never be done, right? I mean, literally, you would never be done. If the entire population of the planet worked on this for the next 10,000 years, we'd still not be done. So that's, and talk about waste of time. That's obviously not something we're going to pursue. What I want to pursue, and will pursue until the horse is completely dead and thoroughly beaten, is it clear that the sample mean is a random variable? Run an experiment by gathering a sample, you calculate your sample mean, and you can assign probabilities to the different outcomes before you gather your sample. No? Yes? Maybe? Okay. By show of hands, how many of you feel that that is obvious? Okay. How many of you feel it's completely opaque and completely non-understandable at all? Okay.
Somewhere in the middle.
Somewhere in the middle, okay. How many of you feel that you understood how we got this particular distribution? Okay, so making sure, one more time, going over this, see if we can't catch everyone. Every single individual, or every single observation gets a column, okay? Every single outcome is listed here, so that every single sample point is listed under our outcomes. Now, for every single sample point, we can calculate a different X bar. The key point there is you can have different sample points that have the exact same sample mean, like for instance here, right? Every single sample point, though, has a probability tied to it. If you collect terms where you have equal outcomes for the sample mean, add those together, you can collect all this into a probability distribution where the sample mean has specific outcomes and probabilities tied to each outcome. So this as a whole is a discrete probability distribution, but X bar is a random variable. The key is you run your experiment, gather a sample, calculate X bar, right? That's fine, but beforehand, you have to assign probabilities. You have to be able to assign probabilities. Okay, well hopefully I really do think this is exactly where trouble starts, because it's not a simple concept at all.
I think it's when you say beforehand, you can assign probabilities. That's that's right there is what we did was after.
No. Okay, after you collect a sample, then you know which row you're in. When I say beforehand, I mean listing all the possible sample points and all the possible outcomes. You have to be able to list the outcomes and the probabilities before you actually gather your sample. But after you gather your sample, you know which row you're in. And all the others are not interesting anymore. Make sense?
So how would you apply that to the SAT score?
Okay, so if you can imagine 30 columns, okay? Can you imagine 30 columns for so x1, x2, x3, x4, all the way up to x30? And then imagine having x1 starting with an SAT score of 400 or whatever the smallest is, and x2 starting with the smallest, and x3 and all the way up, and then we could run through, all the different values of the SATs for the last one, and then you see where I'm going with this? You get an immense list, just incredible. And every single one of those sample points would have a probability tied to it. That's what we list over here, and then we collect terms. Every single X bar, or every single sample that had the same value for the sample mean, we collect and add up those probabilities into the table of outcomes. You can do this conceptually, but you can't do it in practice. Yes? Okay. There's a much, much easier way.
Okay, I was hoping so.
Yeah. Which we'll do, but there is no easier way, I think. There's no other picture I know of that is both smaller and complete. So this is a picture that is complete, right? You have all the different possible outcomes you can get. You have X bar calculated. You have a situation where X bar is replicated, and it becomes a probability distribution. So if you can remember this, so just keep the thinking in your head when you think about problems, it'll be very useful. And if not, it may make life a little tricky, because from now on, we're going to use shortcuts. They're going to allow us to find distributions for X bar that are very powerful, but don't look like this. Okay, so what can we say in general? Well, one really nice property about X bar is that its expected value, the mean of the distribution of X bar, is the mean of the parent population. That is simply because the expected value of sum of xi over n, you can bring inside, so that's just the sum of the E of the X over N. But if you're summing up the same thing N times, that's just N times the mean, so you end up with U. It's not a terribly difficult prospect, although I suspect that might be a little opaque. But you can imagine why this is useful. On average, what it's telling you is, when you estimate X using X bar, you're not, on average, you're hitting the parameter of interest. And that's a nice property. It's called unbiasedness, which we're going to discuss towards the end of the lecture. The other thing you have to have when you deal with a distribution is a standard deviation. So notice we move immediately to the infinite population. The standard deviation of X bar is also known as the standard error. You typically denote that with an X bar subscript. That's equal to the standard deviation of the parent population, sigma, divided by the square root of X. That is why a larger sample helps you get a better estimate. So what happens to the standard deviation as n goes to infinity? Gets smaller. Very good. And in the limit, you get 0. But of course, we're never going to reach the limit within an infinite population. Now, if you have a finite population, you have what's called the finite population correction factor, which sort of changes things. The reason is, when your sample size is equal to the population, you're actually dealing with a census, right? And when you're dealing with a census, you no longer have a random variable. X bar is equal to mu, period, right? Provided you've done everything right. So basically, for a constant, you must have a standard deviation of, what is the standard deviation of the number 4?
Square root of 2.
0.
0, right? The number 4 is not going anywhere. It's quite well anchored to the real number line. So the standard deviation of mu is 0. It just doesn't move around. So when you know what mu is, you no longer have a probability distribution. You no longer have a random variable. You're done. That's what the finite population correction factor does for you. Essentially, you can think of n increasing and your standard deviation, think of this as mu, and this is mu plus the standard deviation, and this mu minus standard deviation of X bar. Well, if you had a finite population correction factor to deal with, then at the point n, you would know what was happening. And uncertainty would collapse, which is a nice thing. You don't, however, need to use the finite population correction factor unless you have more than 5% of the population in your sample. That's what this is saying. Little n divided by the population size is less than or equal to 0.05 means that you don't need to worry about this thing, and you just jump to an infinite population. And that's a really slack requirement, because think about including to the population of the U.S. 300 million people, actually 303 or so now. How large a sample could you have before you need to worry about this?
How many people times 0.49?
Say 300 million.
Times 0.49?
Well, times 0.05, but yeah.
15 million. 15 million.
15 million. Yeah, 15 million. You're not going to have a sample of 15 million on any realistic problem. So typically you don't worry about this. Okay. So how does X bar look in shape? Well, we now have a mean and we have a standard deviation, and the only thing we left over is a shape. And it turns out the shape is that most beautiful of all shapes, the normal distribution, provided you have a large enough sample size. The magic that lets this happen is called the central limit theorem. It's called central because it truly is what bears everything else. If you don't have that, you can't carry pretty much the entire structure in differential statistics. On the other hand, if you have an n greater than or equal to 30, then x bar looks roughly like this. Now it's important to note that the mean and that standard deviation are independent of the central limit theorem, have nothing to do with the central limit theorem. The central limit theorem gives you the shape, and that's very important. Okay, so what does the central limit theorem say precisely? When n goes towards infinity, actually in the limit, then the distribution of x bar becomes normal. But the key question there is, for this particular application, what is close enough to infinity? So, and the answer is 30. But how would you test that? How would you come up with 30?
Is that a rule that was developed empirically?
Sort of, yeah. But not in the sense, not empirically in the sense of actually going out and collecting raw data. But it is it is literally tested and found to hold. How? Any ideas?
If it didn't come from going out and comparing census to sample, then no.
Okay. Well, there's an easier way though. If you, okay, you don't actually have to use data that is out there. You can create your own population. Nothing's stopping you, right? If you're studying a methodology, you just create your own population in a computer, and then you run simulations to see how your model does. It turns out that the actual cutoff is somewhere a little more than 23, but for traditional reasons, 30 is the number that we're going to go by. Most textbooks seem to still use 30, and I don't really see any purpose to cutting that down, particularly because if you have 30, at least you're conservative. There's one other way to get a normally distributed random variable, a normally distributed sample mean, even when you don't have 30 observations. And that is when you have a normally distributed parent population. But the beauty of the central limit theorem again is you don't care how the parent population is distributed. However, if you knew the parent population was normally distributed, you could have a sample of 1, or 2, or 3, and x bar would still be normally distributed. Now, that's a sort of different ball of wax. We'll get to that in a little more detail next week. We're going to focus on the normal distribution. So putting it all together for the SAT scores, remember the population had a mean of 990, just mu, but the standard deviation was much less than 80, it's only 14.6. So now, can you say something about whether or not 997 surprised you? Or Dave, do you still feel that 997 was unsurprising?
I do still feel that was unsurprising.
Can you put it in context?
It's within a half a standard deviation of the mean, so it's right there in the meat of the curve.
Right. Everyone see that? You're perfectly okay to use the empirical rule as a guide here, and something within half a standard deviation, or roughly half a standard deviation, that's not really worth thinking about very much. Okay. So let's apply this. Let's think about the sampling error, and for whatever reason, you could decide that the sampling error you're interested in is 10 points away from the mean. Again, that has to be problem specific. So let's solve this and then we'll take our break. Okay, first of all, how is it that we knew X bar normally distributed?
Sample size is 30.
The sample size is 30, right? So it's more than, greater than or equal to the necessary number to invoke the which theorem?
Central limit.
For limit theorem. And the central limit theorem allows you to treat X bar as if it is equally distributed. We'll repeat that enough times that you're not only bored beyond belief, but you'll never forget it. Even when you're 95. When your birthday is 95, you'll be putting 2 sigma on your birthday cake. I'm kidding about that. Never know. All right. Okay. So we know that this is 990. We want to find the probability that X bar is between 1,000 and 980. And we also remember that the standard deviation of X bar is 14.6. So if you want the probability that X bar is within 10 of mu, you're looking for this area, right? And there's nothing there that's missing in terms of what we've talked about prior to today, so you should quite easily be able to calculate that, or at the very least, point me in the right direction. What's the next step?
Get some z-scores.
There we go. So, this is 10, right? Away from the mean, which is roughly, let's see, 0.68. It's on the next slide, so it's easy enough to check. And if you look up 0.68, what do you find? Okay, so the probability that z is less than 0.68 is equal to 0.7517. So what else do you need in order to find the probability that the sampling error, in other words, X bar minus mu, is less than or equal to 10? That's what this is. This distance here from X bar from 980 to 1,000.
Find the other z-score.
Okay, so that's, since that's symmetrical, we're just going to get a minus 0.68. And what is it?
0.2483.
Okay, so subtracting one from the other, 0.7517 minus 0.2483, we get 0. Thank you. All right, so there is a little more than 50% probability of being within 10 of the population mean. So now you can say something about both how good your sample is and how likely you are to miss, or the point in this case, how likely you are to be fairly close, right? So you might decide that being a good estimator would be being within 10, or, well, that's obviously problem specific. But you're now able to calculate explicit probabilities and therefore judge how good your estimator needs to be. And if you decided that this probability, for instance, was way too low, how could you adjust that? There are at least 2 ways. Actually, I think there are exactly 2 ways.
You can increase your sample size.
And that is the gold-plated answer. You can increase your sample size. Typically, that's what you'd always want to do. But often, there is one other way as well. And that's cheating. Increasing your bounds. decide that a good measure can be within 20 rather than within 10. Okay, questions on calculating that probability? All right, yes.
So you said that, we always have to have a sample of 30?
Now what?
I'm not-
No. Having a sample of 30 allows you to use the central limit there. Treat X bar as if it's normally distributed. If you don't have that, you may still be able to do something, but there are other rules and harder rules that apply.
So we won't know if it's a normal distribution unless we have, does that apply to that?
You won't know if X bar is normally distributed unless, if you have less than 30 observations, you need to know that X itself is normally